Now we have proved the size of a Hadamard matrix can be 1, can be 2, and if it is greater than 2, then the size must be a multiple of 4. This leaves us a question. For each positive integer k, does there always exist a Hadamard matrix of size 4k by 4k? Is this multiple of 4 not just a necessary condition, but also a sufficient condition for a large Hadamard matrix to exist? However, the answer to this question is still open as of now. As of May 2022, this is still open. The latest result is that consecutively, for n equal to 4, 8, 12, all the way to 664, there exists a Hadamard matrix of order n. And non-consecutively, for n less than or equal to 2000 and a multiple of 4, the existence of Hadamard matrix is unknown for only 12 of such n's. And I can give a list of those 12 numbers. They are 668, 7, 16, 8, 92, 11, 32, 12, 44, 13, 88, 14, 36, 16, 76, 17, 72, 19, 16, 19, 68, and 1964. Those are 12 n's. If you can find a Hadamard matrix of order equal to any of them, it will make you famous. And non-consecutively, there's also another result that I would like to mention and also prove. I'm going to write this as a theorem. Hadamard matrix exists for all powers of 2. And now let's prove this. The construction is not too complicated. The complicated part, the tricky part, is the verification of that matrix is Hadamard. Let X be a finite set of m elements, and let the script P of X be the power set of X, namely a set of all subsets of M. You know from basic combinatorics, P of X consists of 2m elements. And we'll label them by C1, C2 all the way to C2 to the power m. So we can call this an indexed power set. Now let A sub ij be the number -1 raised to the power Ci intersection Cj's cardinality. And you observe immediately this is symmetric with respect to I and j. If you switch the role of I and j, it's the same. So this is equal to A sub ji. And let A be the matrix whose entries are A sub ij. Now A is a matrix whose entries are plus minus 1. So to verify that A is a Hadamard matrix, it suffices for us to verify this relation. We only need to verify one of them to be n times In. The other one will follow from there. To this end, we write A as a block matrix, A1, A2, all the way to An. Each A sub I being a column vector. And I want to verify that A sub I transpose times A sub j, which is really the inner product between those two column vectors, is equal to 0 for any I not equal to j. So this is what we're going to verify. Once this is verified, then we'll have this property B, because the off diagonals are all 0, and the diagonal entries are all equal to n, because A sub ij are plus minus 1. So the diagonal entries equal to n follows from just the property A, which is already guaranteed in here. But the verification of this is the tricky part in this proof. Now from our definition, you know this A sub I transpose times A sub j. Now you multiply them, what you get is the summation of -1 raised to the power Ci intersection Ck's cardinality plus Cj intersection Ck's cardinality, where this k is from 1 to 2m. And you want to show that this sum is equal to 0 whenever I is not equal to j. So how do we see this? Now we are going to use some smart counting in combinatorics. So each summand is either plus 1 or minus 1. We better show that there are half of them being plus 1, while the other half being -1. Or we can show that those 2 raised to the power m summands come in pairs. Whenever there's a plus 1, there's a minus 1. And they cancel out. So that is the basic idea. Specifically, here's a trick. Now when I is not equal to j, you know that C sub I is not equal to C sub j. This is because C1, C2, all the way to C sub to m are distinct subsets of P of x. Because they are different, there exists A in Ci minus Cj or A in Cj minus Ci. One of these two cases must happen. Now, without loss of generality, we will assume there exists A in Ci minus Cj. Then we have an observation. We observe that precisely half of the subsets of the m-element set X contain this particular element A, and half do not. Do you see why this is true? This is true because if the subset C contains A, then C minus A does not contain A. So they come in pairs. And here, this notation is not very rigorous. Rigorously, we should write C minus the singleton A. But for convenience, we will omit those parentheses. And now, we fix A. And let C run through all subsets of X containing A. Then, what happens? Then the pair C, C minus A will comprise all subsets of X. When C runs through all subsets of X that contains A, C and C minus A will exhaust all possible subsets of X, all those 2 to the mth power subsets of X. Now let us summarize what we obtained with mathematical notations. This is the same as saying that script P of X is a union of those two element sets when C runs through all subsets of X that contains A. And now let's make another observation. This observation is very important. Fix A, then for each pair C, C minus A, two integers one is the cardinality of Ci intersection C plus the cardinality of Cj intersection C, and the cardinality of Ci intersection C minus A plus the cardinality of Cj intersection C minus A have different parity. But parity would mean evenness and oddness. Namely, when one is even, the other one is odd. So why is this true? This is not hard for you to verify if you remember that Ci and Cj are different, and C is taken from Ci minus Cj. So it follows that Ci intersection C has cardinality 1 more than Ci intersection C minus A. But the cardinality of Cj intersection C is equal to Cj intersection C minus A. It's cardinality. So these are simply because A lives in Ci, but A does not live in Cj. They should be immediate to you. So this guy is one more than this. So they have different parity when you sum up. And follows from this observation immediately that if you look at -1 raised power cardinality Ci intersection C plus cardinality Cj intersection C, and -1 raised power Ci intersection C minus A plus Cj intersection C minus A. This is what? This is 0. Because those two guys have different parity. So let us go back to the thing we want to calculate, the thing we want to verify to be 0. Let's go back to this sum. This sum of 2 to the m summands can be rewritten as which, by our discussion above, by our discussion here, can be separated into two parts. And from what we just discussed, this guy is equal to 0. For each C that's a subset of X that contains A. So we get this sum equal to 0 whenever I is not equal to J. So it follows that AIT times AJ is equal to 0 whenever I is not equal to J. Now since A is this +1 -1 matrix, by definition A is a Hadamard matrix. And we are done. We have constructed for each 2 power a Hadamard matrix.